So I'm starting kind of late, so hopefully you can give me a few more minutes, although I think I can manage it in time. Okay, so today I'm going to talk about non-equilibrium criticality in Quench dynamics. This is work done with my colleague, Titum. So let me start very high level. This is the paradigm of Quench dynamics. We'll start from some initial state, which can be, for example, the ground state of some initial Hamiltonian. And we suddenly change the Hamiltonian, and the state evolves, and something happens. And so the question that we would like to ask is, starting from some initial state and turning on some Hamiltonian, what's the nature of the dynamics, and specifically, what's the nature of the stationary state that is reached at long times? Okay, so now it's widely understood that a generic quantum system thermalize. How is this possible? Because one is a pure state, always remaining a pure state. The other one is a thermal state. The key is that if you look at local observables, working. Okay, if you look at local observables, things look like a thermal quantity, and you can describe this in terms of some reduced density matrix that describes the state of the system. And this T is also given in terms of how much energy we imparted in the system. By the way, if you have any question at any point, just interrupt me. Okay, integrable systems provide a different paradigm. They don't thermalize, so the reduced density matrix is not given by a thermal state. So instead of a Gibbs state, they will be described by something that's called GGE, that keeps track of conserved quantities. Okay, I think so far so familiar, so good. But the question that I would like to ask is, what if we don't insist on full thermalization in integrable systems? So I don't insist that the full state would be just E2 minus H over T in the sense of reduced density matrix. But what if we ask the following question? Can we have thermalization even in integrable system, but at long wavelengths and long times? So this is a much more conservative question than insisting that the full state has to be a thermal state. So if this is the case, if we have thermalization even in integrable systems, all I'm asking for is whether we have some effective temperature at low frequencies. So I don't insist that the entire state should be a thermal, but only at low frequencies. It turns out that that's actually the case in many cases. For example, an example is 1D Bose gas, that you just have one-dimensional gas and just split this into two different halves. So the model is actually described by Lottinger liquid theory, which is exactly solvable, hence integrable. And there is a ton of theory work and also experiment which lead to the conclusion that, in fact, in this integrable system, you find an effective temperature at low frequencies. So even in this integrable system, you find an effective temperature upon the quench if you wait for a long time and only look at properties at long wavelengths and low frequencies. In fact, an effective temperature emerges in this system. Okay, so the way to find this paper, for example, you can look at how much bosons we have in the system, and you can see if at the thermal state, if you look at the states which have low K, low momentum, you can compare the population of these states with a thermal state, and that way you can identify the effective temperature. But you only do that for the sector of states that are defined at low K, low frequencies. Right. How recent? Okay. I see. Okay, sure. So here, I guess I'm not saying exactly that all integrable system would find an effective temperature, but I'm just giving you an example that even an integrable system that everybody has told us nothing really thermalizes. In fact, there's a sense that if you look at the right sector, things actually thermalize. Yes. Right, so it depends on the observable. So if you look at the observable that are defined at low K, then you would find this property. Maybe as I go on, this would actually become more clear because in the context of this talk, I will actually talk about an example that exactly shows all these properties. So that would become more clear. But if it's not clear, please ask me the same question then. Because I don't want to, it is about their experiments, I don't want to defend their experiments. I want to defend my own work. Okay, so let me at this point just pose this as a question. Integrable systems generically do not thermalize in the strong sense of thermalization, but I just want to pose as a question, do they effectively thermalize at long wavelengths and times? Or alternatively, can they not thermalize in some sense that even at long wavelengths, they do not find this non-thermal behavior? And specifically, can we identify some non-thermal critical behavior in the system? And this is particularly interesting because the critical phenomena are associated or sensitive really to long wavelengths and frequencies. So if you're interested about this, you're certainly interested in the limit of long wavelengths and low frequencies. Okay, so this is in the context of the work that I'd like to present here. The model I'm going to consider here is really super simple. It's perhaps one of the simplest many-body systems you can imagine. But even in this system, you'll see that there is a really rich structure. Okay, so this model is LMG. This is basically a fancy name for an infinite range Ising model. In this case, the Ising model is, so you have Ising interaction along the x direction as well as the y direction. In principle, they can come with different coefficients, gamma x and gamma y. And there's a transverse field here, delta. And so there are n different spins. Okay, so this simple looking model has application actually to many systems ranging from nuclear physics that was first invented to BEC and trapped ions. Okay, so let me first present, before telling you anything about the Quench dynamics and non-equilibrium stuff, let me just tell you what's going on in equilibrium. So in particular, what happens at zero temperature. In fact, this model is known to give rise to a simple phase transition. Or not so simple, but this is because the model is infinite range, you can find this phase diagram exactly from in field. So as you can see, this is, okay, part of it is cut off. I apologize for that. So this is J times gamma x over delta. This is J gamma y over delta. So as the Ising interaction along any direction becomes stronger, you go into an ordered phase, which is an Ising order phase. You have a Z2 symmetry that's broken. And for small values of the Ising interaction, this is just a disordered phase. So the phase transition is defined by this equation. So when delta, depending on which one is larger, when delta is just J times gamma x, or when delta is J times gamma y. So one line is this one, the other line would be the other one. Okay, so this is basically just the same statement, but I just want to show you some figure that how this works. Actually, just to confuse you, I've changed the axis here. Sorry for that. This is J over delta, and this is delta over J. And here I restrict myself to gamma x being 1 and gamma y being 0. So I basically just move on this line. As you move here from left to the right, here you move from right to the left. Basically, the Ising interaction becomes stronger and stronger. And finally, you have this phase transition that the spin finds a finite expectation value. Yes? I mean, I did not make any assumptions about the nature of long range or short range interactions. It can be any many body system. Sorry? Oh, this is an integrable model. So I mean, you're right. If this was a chaotic model, if I have long range interactions, then I have to worry about this. But this is an integrable model, so it's even worse. So this is not going to thermalize. Do you see what I'm saying? Okay, for now, just consider if a simple model I consider that I'm going to do some Quench here and tell you about some interesting stuff. Okay, so since this is actually an infinite range model, I can describe everything in terms of a collective spin. So the collective spin is just the sum of the sigmas, and then you can write the Hamiltonian in terms of the total spin. Okay, so this is a very simple set of observations. In the ordered phase, The total spin normalized by n is just order 1. That's the definition of the ordered phase. In the disordered phase, the expectation value of Sx itself is 0. But if you look at fluctuations, so this is the average of Sx squared, is actually proportional to the square root of n, but this is not really surprising. This is generically the case. The fluctuations are proportional to the square root of the volume of the system. So this is non-critical fluctuations. And at the quantum phase transition, so remember, this is the phase diagram at t equals 0. It turns out that it's not this case or the other case, it's something in between. So again, the expectation value of the spin itself is 0, just because we are right at border. But the fluctuations are actually proportional to a power of n. And that exponent is given by 1/3. So that's an exponent that defines the critical quantum fluctuations. And finally, a thermal phase transition, which I have not shown here. So if I want to put temperature or add temperature on this plot, I have to add another axis for the temperature. But there's a thermal phase transition as well. And it turns out that for that one, the fluctuations is actually different, is governed by a different exponent, 1/2. So even in this simple model, which is sort of mean field, you can see that the fluctuations at the phase transition, they can distinguish between the quantum case and the thermal case. Okay, so everything I described so far is just equilibrium. Now let's do some quench dynamics. So this is a Hamiltonian, and like the paradigm that I told you in the beginning, I just start from some initial set of parameters and quench it to some final set of parameters. And so gamma x, gamma y, and delta change from some initial value to some final value. And I just set j to 1, and that way I set the time scale. That's not important. And specifically, I want to quench to this point because this is a point that you have fluctuation in the system, and in principle, this fluctuation can give you new critical behavior. Okay, let me start by doing something rather simple. Let me stay kind of away from this phase transition. And so that way I can use an approximation that goes by Hossan-Primakov. Many of you have probably seen this. Very simple, just replacing the spins in terms of bosonic variables, in this case, just in terms of x and p for the harmonic oscillator. So this is the usual commutation relation. And if you do it this way, then instead of a spin model, you have just a harmonic oscillator, and the quench dynamics in terms of this Hamiltonian would be just quenching the mass and the frequency of the harmonic oscillator. So very simple. We can almost solve everything exactly. And so again, if you quench it to, so starting from the disordered phase and quenching to the point also in the disordered phase, the expectation value of Sx remains 0 at all times. But you can look at the fluctuations, and it turns out that if you solve a problem in terms of the harmonic oscillator, evolve it to infinite time, and compute the average, and also forget about fast oscillations, this gives you something that's proportional to 1 over omega squared. And this omega is nothing but the natural frequency of this harmonic oscillator. So you can notice that this is actually similar to behavior at finite temperature. So this theorem tells us that at high temperatures, the average of the potential energy should be proportional to T. So this way, you just see the same relation if you impose some fictitious effective temperature in the system. So just by doing this simple comparison, you can identify what the effective temperature is. So just you look at this, you identify what shows up here, the prefactor, and that defines the effective temperature. And let's now look at this effective temperature and how it behaves depending on the quench. It turns out that this effective temperature would be very different depending on what your initial state is. Okay, so let's start from a generic situation that I don't know, and I don't do any fine tuning for the initial state. So I can start from some point in the disordered phase. Here, for being specific, I start on the same line, but it doesn't matter. Any point in the disordered phase, just looking at the relation that I have for the effective temperature, you find a constant effective temperature. And this looks like it's something that's consistent with effective thermal behavior. But let's actually look at the different case that I call type 2. This was type 1, the generic case. For type 2, if I start from the same line, which is actually the phase transition, and quench it to another point on the same line, I find an effective temperature that vanishes. So this actually likes something else, the quantum case. And finally, if I quench not from the same line, but from the other line, I find that the effective temperature actually diverges. So depending on what initial state I choose, and especially if I fine-tune it, in the case of type 2 and type 3, I find completely different behavior for the effective temperature. Okay, so this is just a simple observation based on some simple analysis, but now let's do something more serious. Let's actually, just to be more convincing, let's do some numerics. I will argue that this effective temperature going to infinity is actually results in some non-equilibrium behavior. Yes? Yes. Any other question? Okay, so let me start from type 1. So this is starting from some point in the disordered phase and quenching to the critical point. So, and here you notice that I chose different system sizes ranging from 2,000 to 9,000. And you can see that, so again, as I quench the critical point, the expectation value remains 0 at all times. So nothing interesting to be said about the order parameter, but you can look at the fluctuations in the system, and it turns out the fluctuations depend strongly on the system size. And in fact, you can see that the fluctuation in a way diverge with the system size. And also there's a time scale. If you look at this peak, you can see that the peak also moves to the right. So the time scale also in a way scales with system size. Actually, it turns out that you can rescale this, or you can, by appropriately rescaling time and fluctuations, you can collapse all these different curves on the same curve. So if you, rescale this by this quantity and rescale time by n to the 1/4, as you can see it here, all the curves actually collapse on top of each other. And I hope that you still remember this exponent, because I showed you this exponent a while ago. And I said this is exactly the same exponent that you find in the thermal phase transition. So remember, the quantum exponent was 1/3, the thermal exponent was 1/2. And in fact, you can see that our simple game that we played that gave us constant effective temperature is actually consistent even with the exponent. Okay, so again, I emphasize that this is only an effective thermalization. The state is not really a thermal state, only in the sense of the critical behavior and the critical exponents and so on, which are only sensitive to low frequencies or long wavelengths if you have short-range interactions. Those are exactly the same as you would find in a thermal phase transition. Okay, let me look at the now type 2. For type 2, I just repeat the same game for different system sizes. Again, you have some scaling, but let me quickly compare to this. Here you can see that the fluctuations started from some small value. You can see it here, but they just they become very large over time. In the case of quantum, that actually doesn't happen. They start from some finite value. They don't deviate that much. And again, you can do some scaling. And in this case, you find that this exponent, the 1/3 exponent, governs the behavior of the system. So again, this is actually consistent with what I told you before, that the effective temperature in this case becomes 0. Yeah, yes, that one is different. That's the dynamical exponent. And in fact, the dynamical exponent, you can also look at the dynamical exponent, and it turns out that at finite temperature, the dynamical exponent is 1/4. And at 0 temperature, the dynamical exponent is 1/3. And that's also consistent, right? Okay, so in this case, actually, it turns out this is maybe not so exciting, because it turns out that if you look at the system, it's not really that excited. Although you quench the system, somehow the system has a state kind of low in terms of the excited states. Okay, now let's actually look at the most exciting situation. That's type 3. So this is starting from one critical line and quenching it with the other critical line. And in this case, you see that things diverge and diverge even more. If you compare to the previous one, you kind of look at these numbers become larger and larger. And again, you see that fluctuations diverge, time scale diverges, and this time you find a new set of exponents. So in this case, you find that to collapse everything on top of each other, you have to introduce this new exponent, 2/3, which has no quantum or thermal counterpart. And also this dynamical exponent is also, that one is neither quantum nor thermal. And this was the case that was the most exotic one because it gave rise to this infinite effective temperature. So this is indeed non-equilibrium critical. Let me show you one more thing. Here, what I showed you was basically the dynamics of fluctuations. As time evolves, yes? It's actually finite, but because it becomes so large that you can't quite see it here. So it's some, yeah, the all is at some finite value, right? Okay, so far I looked at the dynamics of fluctuations, but now I want to look at different quantity. I want to wait long enough that I go to the stationary state that not much is happening, or at least it looks like it. But in the steady state, I want to look at two-time functions. So two-time correlation function and the response function. So one is basically the commutator between the two fields, and the other one is the anti-commutator. And I want to fix T1 and T2 such that they're much larger than T2 minus T1, just making sure that they're large enough or they're long enough that we are already in the steady state. And if you repeat this, so here I just present a single curve. I've already did the scaling. So if you choose the right scaling, right over here, even within the steady state, so this is not just the fluctuations, but the correlation functions within the steady state are also described by the same set of exponents. Okay, so not only the fluctuations, but also the correlation function and the response function defined within the steady state are governed by the same exponent. So which I call alpha and zeta. So alpha for the exponent of fluctuations and zeta for this dynamical exponent. And so for type 1, which is the most generic one, starting pretty much from any point in the disordered phase, you find the usual thermal exponents. For the type 2, you'll find the quantum one, but that's not surprising because you haven't gone too far from the quantum ground state. And finally, for type 3, you'll find new exponents, generally new exponents that have no table in equilibrium reports those exponents. Okay, universality, how much time do I have? +5? +5, okay. Okay, actually, I think I'm good. Okay, so. I'm actually going there, yes, I'm going there. Yeah, you got me to a slide too early, yes. By the middle, you mean a diagonal? That's a good question. We didn't look at this, but I know that you were asking this question because that's a good question. The symmetry changes because that one doesn't have a Z2 symmetry. That one actually has a U1 symmetry. So the description of the problem changes. So we haven't looked at this, but yeah, that's it. Okay, so I want to basically spend one slide telling you where this exponent. So I showed you numerics. What would you believe numerics? So this is my argument that how these exponents come out. This is the simplest argument that I could make. I mean, in the paper, we're more rigorous, but okay, so my argument goes like this. In order to identify these exponents, we have some, we need some effective field theory, and let me identify my field by X, which represents, that's the Holston-Primakov field for Sx. So we already observed divergent fluctuations. So let's use this knowledge and rescale X to be this quantity. So now X is of order 1. And let's just do the same thing with time. So time, we also notice that diverges with the system size. So let's also scale out that divergence. Okay, now let's look at the initial state first. The initial state starting, so this is only for type 3, although we can work it out for all types. For type 3, the initial state has divergent fluctuations along Sy. So Sy translates in this language to P, and P in the language of harmonic oscillator is nothing but X dot. So if you want to get this exponent for the initial state, and now you can just replace for X by this capital X and T by capital T here, you'll see that this only works if your exponent satisfies this condition. So that's the scaling or the relation that comes from considering the initial state. Now, this is just the initial state. This is one relation between two exponents. To find the other relation, I have to look at the dynamics. So this way, I have to add these nonlinear terms beyond just a linear term. And in the end, the Hamiltonian would look like this, which I don't think would be that surprising. You have a harmonic oscillator, and on top of that, you have a quartic potential. Now, at the critical point, that term goes away by definition. You've seen this in Landau-Ginzburg type Hamiltonian. So we're left with these two terms. And again, P goes to X dot. And if you want to make this a scale invariant using these three scale variables that I have given you here, if you want to satisfy this condition, it turns out that you need another condition between alpha and zeta. Okay, so if this was too fast, you can ask me, or we can look up the paper. But the point is that to identify these relations, which actually give you these exponents, I needed both the initial condition as well as the dynamics. So this is in the sense of the boundary critical phenomena that was a field itself that considers the critical behavior near surfaces and boundaries. So this is in the same spirit, although in this case it was infinitely simpler because of the infinite range nature of the model. Anyways, so we can extract these exponents. And now coming back to your question, let's also identify an effective temperature. I told you that the temperature diverges, but what does that exactly mean? So, okay, to do that, I need the correlation and the response function. So the correlation gives you information about fluctuations, and the response gives you information about dissipation in the system. And in equilibrium, not in this problem, but in equilibrium, you have this relation, which is a fluctuation-dissipation relation. At high temperatures, again in equilibrium, at high T or low frequency, if you're interested in low frequency at any finite temperature, you can, write this quantity in terms of T over omega, and H bar goes away. I think this should look familiar to many of you. Now, outside equilibrium, let me just take this relation and let me just replace the temperature by some effective temperature that may depend on frequency. Let's see what happens. Okay, so I have I actually have the scaling relations for the correlation and the response function. So in principle, I can calculate this. And when I calculate this, I find that the effective temperature, you can compute this. You can do some scaling, thing. And finally, you can take the limit that omega goes to 0. And it turns out that the effective temperature actually diverges for this type 3, diverges with the system size, but diverges with something that scales like this parabola sub-extensively with the system size. Okay, can we check this with numerics? It's actually kind of hard, because if you want to check this against the numerics, numerics is defined in the time domain, and it's already kind of hard to go to longer times. But you need this, if you want to verify this relation, you have to be in frequency space. But let me cheat a little bit, not too much, just cheat. Let me go back to this relation that I had in frequency space. So for this form of relationship, I think if you just stare at this for a second, it becomes clear that you can also write this in the time domain in this way. So this just means that chi of t for the response function is proportional to the first time derivative of the correlation function. And the constant of proportionality, this constant is just 1 over t. Okay, so now I'm going to use a different notion of the effective temperature that could be time dependent. This is not the same definition as one you define in frequency space, but still, people have used this. It has been, useful in some contexts. And if you do this, you actually, so now let's look at the numerics. You can look at t as a function of t. You see some slight dependence on time, but not too much. This is for a fixed system size. So this just gives you a feel for this effective time-dependent temperature. And then you can look at these different system sizes, not just one, and you can see that this is indeed a good fit to n to the 1/3. So we can check something like the divergence of the effective temperature as a function of the system size. Yes? Yeah, because I actually care about the limit of low frequencies. That's a limit I'm most interested in, because also the properties of the system. Sorry? So this way, I mean, actually here we can do it self-consistently. So it turns out that in the end, the effective temperature scales with the system size like into the 1/3. So you need to choose any omega that's much smaller than n to 1/3. But actually, you don't want to go that far because omega being of order 1, already you see the macroscopic dynamics. You don't want to see that. So you want to be in the regime that omega is much smaller than 1 in the units of j. I think I'm almost done. Okay, so this is just a summary. Nothing really new, but depending on the quench that you're doing in the system, you find different exponents, and so these behaviors are actually, everything is consistent with each other, which is nice. This type 1 is consistent with having an effective finite temperature that's a constant. Type 2 is consistent with an effective temperature that's 0. And finally, type 3, at least something very exotic happens in terms of the effective temperature, which is also responsible for these non-equilibrium exponents and critical behavior. Okay, so I just emphasize one thing that effectively, so again, this word is sort of the main point of my talk. Effectively, this is thermal, and this is kind of, it does not mean that you have to do some fine tuning, but in the other two cases, when you find 0 temperature or this non-equilibrium behavior at diverging temperature, you need to do some fine tuning. So you have to start exactly on this critical line, or in the other case, you have to start, it actually doesn't matter where on this line you start with, but it's important you start on this line. So to find quantum, you have to do more fine tuning, but again, this is probably consistent with your intuition because quantum usually requires more fine tuning, like taking the temperature to 0. Here we don't have any sense of temperature in the system, but you know, the fact that we have to do some fine tuning is still the case. Okay, so let me just summarize. So integrable systems generically do not thermalize in the strong sense, but they can still effectively thermalize. But if you do more fine tuning, they actually become non-thermal, and by non-thermal I mean either the this kind of behavior at 0 temperature or the non-equilibrium behavior. Okay, so LMG model already shows a rich non-thermal behavior, and I'm already talking to some experimentalists to actually do this in trap ions. But the more important question is what other models, because this is just one example. And in principle, one can ask this question about a wide range of models, not just LMG models. Okay, with that, let me just finish and thank you for your attention.
Okay, so are there any questions? Comments?
You mean ordered or disordered? Oh yeah, so I didn't do, yeah, that's a fair question. And there was a very good reason that we didn't do it. If you do it from the ordered phase, everything is kind of governed by mean field. And this is being done in the literature for forever. Many people have done this, and they've defined a phase transition, which is different from the sense of phase transition that I've defined here. For them, they look at the mean field dynamics, and they look at the time. Right, so if they have some Sx of t that changes with time, they take the time average of this, and depending on whether this average is 0 or not 0, they define a phase transition. The reason that I stayed away from this is because I did not want to have mean field. I wanted to have something more interesting. So again, it depends on, I don't think so. Why? So mean field in the sense that this is infinite range, but this is infinite range of a spin 1/2 system.
It's to spin 1.
That's a good question because the symmetry changes in that case. So every time the symmetry changes, I mean, in principle, that makes the phase diagram richer. So in principle, you have more things to say. But I don't know. I haven't looked at it. Right? But that's in the spirit of the question that I put on the Outlook, that in principle, there are many interesting models that one can Okay. Numerous, how do we do it? My colleague did it, but I think, I mean, we're not doing anything exotic. We just write down the, so I mean, one thing that helps is that the total spin is conserved, right? So we limit ourselves to the highest spin, which would be n over 2. And in that sector, we can do numerics, but basically we just write down the normal equations for the dynamics of a spin system.
Yeah.
It's typical for your model, or do you expect them to be like for some other model that you take up, which is also integrable, and then you can also have some phase diagram? Do you expect the same kind of exponents to come out, or are those exponents like model dependent, or is that a universality class? Or?
It is it is indeed
I mean, since you've only tried like one particular model, the LM model that you have, like how can you?
But yeah, I mean, if you
expect it
perturb
from-
this model in some way, I assume, I can't tell you exactly what kind of perturbations, but if you make certain perturbation in this model, I don't think that's going to change the exponents. So
Okay.
in that sense,
And
it's universal.
does this all-to-all coupling that you have,
Right.
is it critical for this thing, for this universality to
I
happen?
don't think, actually, that's, again, sort of the question that I posed in the outlook. I don't think that's important. The thing that's important is the dynamics is not chaotic. So that's what's important. The infinite range was just some simple model that we could do almost everything exactly. So we could see everything, just, we can just look at them face to face. So that was very assuring. But in principle, any system that has some sort of integrability should be qualified.
Any other questions or comments? If not, let's thank speaker again.
Thank you.